Hello, this is a video. It will be an illustration of multivariate regression. And what we're going to do is use the HBAT data set to run through this. So this will be just a series of steps to illustrate the evaluation of a multivariate or multivariable regression. Let's just get started. We know with the HBAT data set, the x19 variable here, if we go to variable view, we'll look at what these are, but if we go to x19, we know this is satisfaction. So we're going to go with satisfaction, and this illustration may be available through the textbook too. So you can look at the textbook, and you can also take a look at this video. You have access to the data, so you can walk through this process as I do it if you would like. But this will be just the general rundown of a basic multivariate regression that is pretty straightforward. So we're going to go to Analyze, and then we'll go to Regression, and then we're going to go to Linear. And I've already put some of the variables in here, so I'm just going to blow that up a little bit. Our dependent variable will be satisfaction. And then we have a series of independent variables. Now, before we get to deciding what our independent variables will be, there is likely going to be a good amount of work that's involved with the process of analyzing our variables. Maybe we have already performed a correlation matrix to determine which variables may load or may predict, if you will, satisfaction. As a very side note here, whenever I do analysis like this, I almost always begin with a correlation matrix. So a correlation matrix will tell you a lot, and if you recall, regression is largely based on the correlations between variables. And so the key then is, if you do a correlation matrix and you have variables that do not correlate, then there's no use in running a regression. So read the correlation matrix, and then that will inform you, before you ever do the regression, which variables will very likely be significant. What it won't do is necessarily tell you which variables are collinear and share variance together. So that's something that we need to check and double check a couple times. Okay, so I have my independent variables here. I have my dependent variable that I'm going to use. We're going to pop over here to statistics. We have our estimates, which should already be chosen, and we want model fit. But then we also want to choose these others here: descriptives, part and partial correlations, collinearity diagnostics. And then to help us identify outliers, we'll do a case-wise diagnostics. Now, a question comes up: how much outside the norm should an outlier be? And again, this is a researcher decision here. We're going to put 3 standard deviations, but that's pretty far outside the norm. If you want to be stricter, you would maybe limit that to 2 or 2.5 or something along those lines. So we'll just keep this the way it is, just so that we'll use this as an illustration. But this would be the case-wise, so this would be by respondent, like respondent by respondent diagnostics. Okay, so we'll click OK. With our plots, we're going to do a couple things here. Number 1, we're going to choose a normality plot. Number 2, we're going to choose the standardized residual and the standardized predicted variable. And basically what's happening here is we're going to create a plot between these two statistics, and it's going to show us the deviation of a predicted variable from an actual variable. And so there'll be a diagonal line, and there'll be some predicted variables, some predicted outcomes that are off that line a little bit, and the degree to which they're off the line shows how far away the residual is from the predicted value. Okay, so the residual value then, if you'll remember, is simply the difference between a predicted value and the actual value. And the goal of multiple regression is to minimize that. That's what least squares does. The least squared errors is like the smallest residuals possible. It's basically what the goal is of the model. That's the model objective. Okay, so this helps us identify what that, it helps us just take a picture of that. Okay, other things, save. We've done this before, and actually in a prior version here, I've done this where we have the Mahalanobis and Cook's distances. So the Mahalanobis and the Cook's distances should be checked here. Checked right there. Okay, so that'll be good. We want to be able to do that. Let's see, is there anything else here? We want to save that. We've got our plots. I think that's all we want to really do. And then we want to run our data and analyze it. Okay, so I'm going to go OK. And we have our output variable here. Now, one thing I will do is I'll slide this output a little bit over just so that we can see there's this and this. These two are new variables we just created. I had done it before, that's why there's one already there. So Mahalanobis and Cook's 2 is what we just created for this. And we may need to look at that. We've talked a little bit about outliers before, and that's where we can identify those. So we may want to do that, but we'll play around and we'll see where we get to. Okay, so this is the regression then that we just ran, and you'll note that there's a descriptive statistics box. So we have our means and our standard deviations for each of the variables that we've had, including the DV, this satisfaction. And then we have our correlation box. So now what we want to look at here, if you've not done a correlation already, it will be reported here. Now, again, as I mentioned, I always do a correlation matrix first, and that helps me predict what I can expect to find in my regression. So there's not usually huge surprises for me when I actually run the regression. I typically know what I'm going to find. And so here, what we're going to look for is, if we look at satisfaction, which is our DV, we want to see fairly high correlations between our DV and each independent variable. So our satisfaction with product quality, commerce activities, complaint resolution, and so on. So these are all 0.5 or higher. We've got this one here, 0.283, which is pretty low. So 8x7 e-commerce activities. If I'm going to run this regression, I'm going to probably find this one variable to be not, this one may not be significant, or it may not be very strongly significant, or the coefficient that's predicted, that's estimated rather, will probably be pretty small compared to the other ones. Okay, so number one, correlation matrix, look at the dependent variable and independent variable correlations and confirm that they're fairly strong. Number two, what we want to look at is the inter-independent variable correlation. So in other words, look at the correlation between independent variables, and these we want to have in absolute size or magnitude to be pretty small. Right? So we don't want, for instance, there to be strong correlation between independent variables. So if we look across here, we're going to look at like x6 and x6 with, for instance, x7. That's not that 0.13 is not that bad. 0.10 is not bad. Now here we have a 0.477. That approaches a concern where x11 and x6 are correlated at 0.477. Now, obviously, we're going to have some correlation, but we don't want to see a lot. So that's something we're going to look at, and And we're going to go through these others. So x9 is next, or x7 here is next. We have 1, 3, we already saw that. 7, 9, 2. See, so x7 and x12. We already knew x7 had a fairly low correlation with satisfaction. Now we see it has a very high correlation with x12. This tells me that these two variables share a lot of correlation, and they both may not be necessary in my regression. So for instance, I may be able to take out like x7 because it's being explained so well in x12, and I probably am not going, my model is probably not going to suffer a whole lot, in other words, yet I'll gain a degree of freedom and my model will be more parsimonious. So that's just something to look at. X9 and X16, those look like, see, we have a 0.757. We also have a 0.561 here with X9 and X11. So that's problematic, or potentially problematic. We'll just have to see. It may be no big deal, but those are things that we're going to look for initially, and that's something that I would make note of moving forward. Okay, so now we're going to look at additional tests for collinearity or multicollinearity with what we call the tolerance and the variance inflation factor. So if I scroll down and I look at this coefficients box now, way over here to the right, we have the collinearity statistics, tolerance, and VIS. Now, what tolerance is all about, that's like a measure of how much variance is explained by is attributed to each one of these variables. So this is a deal where we want it to be fairly large. We want something fairly large here. So the cutoff here is actually 0.1. So anything above a 0.1 would be sufficient in helping describe our dependent variable. Okay, so anything above 0.1 under tolerance is going to be, again, sufficient for helping explain some of the variance in satisfaction. The VIF is another term, and it's related to tolerance, actually. So the VIF is actually 1 divided by the tolerance. 1 divided by the tolerance. So the cutoff here is what we want is anything below a 10. A 10. So this is like 1.3, 2.7, 3.0, 2.0, 2.9, basically 2.6 or 2.3. Those are all easily well below 10. So they are acceptable. They all explain some of the variance that's going on. So the VIF, variance inflation factor, we don't want those to be significantly high or above a 10. That's basically what we're looking for. So below a 10 on the VIF, above 0.1 on the tolerance. So we're good. So we have variables here that there may be some collinearity going on, but we need to kind of confirm more so. We need to look at this in a greater way, and we'll just we'll look at the results here in just a second. But from a VIF perspective, a tolerance perspective, we have variables that are explaining variance and not overstating variance too greatly. So we're going to continue to move on. Okay. Next, we're going to look at, so this is like, we looked at the correlation box, we looked at tolerances and variance inflation factors. That was second. Third, we're going to look at our plots. Now remember I mentioned the PP plot, or I mentioned this idea of a 45-degree angle, and based on the dependent variable of satisfaction, we have expected probabilities and we have observed probabilities. And what you again want is something that's fairly close to this 45-degree angle, because what it suggests is that the residuals, or the expected values based on the residuals, are fairly close to the observed values. So again, so we want a line here that's fairly tight along this one because it means that the residuals match the actuals. The residuals are fairly small when compared to the actual observed values. So that seems to be decent with a few exceptions here in terms of things going off. And you know, the patterns will often be where it like loops around or something like that. And there's not a lot of looping going on here. There's some deviation, but that is what it is. The other thing that we'll look at here will be the regression, standardized residuals, and the predicted residuals. So this is what we asked for to be plotted specifically. And what you'll generally look for is a clustering of your data. You'll look for anything that's falling abnormally outside of the kind of a circle or just kind of a grouping, if you will, all by itself. And those would indicate outliers. And then the other thing that you're looking for is anything that would be beyond a 3 here, because these are standardized values. So maybe you think of these as like standard deviations or standardized distances. And again, we asked for outliers outside of 3. And moreover, when we look at this, we do not have here in our analysis a case-wise diagnostics box. So if we had outliers that fell outside of 3 deviations of the mean, then we would actually have a box here, that a table, in other words, that would tell us what was going on with those outliers. But we don't have any of those. So it's not like we're that worried about what's going on. If we did, so this is a good point here, if we had outliers, then what we would do is go back to our data and we'd look at this Mahalanobis distance and Cook's distance. Now, the Mahalanobis distance is a much stronger test than Cook's. So if we looked at this, we could actually take our data and again, I'm going to get rid of, just for simplicity purposes, I'm going to get rid of these first 2 variables because I did them earlier and we don't need them. These are the ones we just ran. So what we could actually do is go to transform, sort cases by the Mahalanobis distance. And I'm going to do it in descending order, only because what we can do now is look at the data, and we've got the size here going on. So this is the largest is 16.15. And again, this is a test that you can do for outliers. Okay, so for Mahalanobis distance, we want to divide this by the number of independent variables that we have. All right, so just let me grab this over here just so that pull this over just so the MD squared. So this is the Mahalanobis distance squared divided by, oopsie, let me pull that down, divided by the number of degrees of freedom. So in this case, the largest Mahalanobis distance is 16.15 divided by 6. So because the degrees of freedom in this case, you use the number of independent variables. If you remember that, we have 6 independent variables. So we got 16.15 divided by 6. So this is going to equal 2.69. So 2.5 is the cutoff for small samples. 3 to 4 is the cutoff for large samples. Okay, so we have 100 in this sample, in this data set. So we're really, that's not a small sample. It's not a super large sample, but it's not a small sample. And again, we just calculated the very largest outlier, if we had an outlier, the very largest respondents MD Mahalanobis D squared score divided by independent variables is 2.69. So even though that would say that maybe that's an outlier for a small sample, it's not an outlier for a large sample. So couple ways then to identify outliers. We certainly want to look at the Mahalanobis distance. The Cook's distance is also something that we can look at as well. Although again, it's not as strong of a case. In other words, it's not as strong of a of something that we could as strong of a test. And with the Cooks, we want something larger than 1 even to be able to say that that's going to be an outlier. So if we go in the output again, if we go number 1, look at this plot, look at the scatter plot and see that there aren't any huge outliers way outside, and there are not. Then come back up, and we're going to look for right here residual statistics. The Mahalanobis distance, the smallest was a 1.07. We know that the largest was a 16.15. So we already investigated that and found that even the largest quote-unquote potential outlier is not an outlier. Then you can also look at the Cook's distance, and again, the cutoff is 1 here, so there's not anything that we're really going to be concerned about on the Cook's distance either. So we don't have any outliers. We're not that worried about we're not, you know, we looked at the item multicollinearity. We're not too worried about that. So now let's look at the actual model results, because this is like the fit statistics, right? This tells you how well the model fits and whether it does so efficiently, and that's a big deal. So the model statistics here, the R value. And you'll remember there's R, that's usually a lowercase r, which means correlation between 2 variables. But this capital R is the variance explained in the dependent variable by the independent variables. Okay, so the 6 independent variables explain 0.893. You can maybe think about that as maybe percent, but it's the R. Now, the R squared and the adjusted R squared, importantly, adjusts the R squared based on how much inter-item correlation there is among the independent variables. So in other words, if there's a lot of multicollinearity, the adjusted R square will drop the R dramatically. Here, it doesn't drop that much. It's not that big of a change between 8.9 and 7.8. But if we saw something where it dropped down to like 0.3 or 0.4 or 0.2 or something, then that would say, wow, we've got a lot of collinearity going among our IVs. So we need to double check, see what's really going on. But this is super strong. This is a good model. This is not a bad model at all. The ANOVA, you've probably seen before. The ANOVA predicts or creates what's called an F statistic. And the F statistic measures the overall model significance in its ability to predict the dependent variable. So it doesn't tell us which variables do and which variables don't predict satisfaction. It doesn't tell us how well independent variables do in doing so. It tells us the overall model fit, the entire model as a whole. And so again, we have 6 degrees of freedom here. We had, so we have clearly significance going on. That's good. We need to have that. But the F statistic's not very, It's actually not a great. I mean, it's almost always significant. If you had even if you had just one variable that helped predict satisfaction, then we'd have a significant F. So F is not really doesn't really tell us a lot, but it's something just to check off the list to make sure we're cool with. And then finally, we want to come to these correlations or these coefficients. Excuse me. So you're going to have this box here, and I just want to be clear about what is happening. So we have our unstandardized coefficients. So this is what you use when you create your model. This is the coefficient that you used when you actually use your model to predict satisfaction going forward. Because I mean, the goal is we want to forecast satisfaction and we want to know what's going on. We want to be able to predict satisfaction. So we use unstandardized coefficients to do so. When we use the standardized coefficients, so we use the standardized betas here, those we need to be able to, we use for comparative measures and for significance. Okay, so we look at the size of the beta as it deviates from 0. So this is like a t-test. So 0.428, how far away is that from 0? And is that a significant distance? Okay, so the difference between 0 and 4.28 is significant. The t-statistic for this distance and this data that we have is 7.806, and that's clearly a large t-statistic, so it's significant. Okay, all of these are significant. X16 is marginally significant if you're using like a 0.05 or 0.001 cutoff. So this one here, if we're using a 0.10 cutoff, then it would be significant, and it is. So from a standardized perspective, look at the size of Salesforce image. It's 0.703. Product quality is next. So these two are the strongest variables. They have the strongest influence in predicting, the greatest influence in predicting satisfaction. In fact, they're 2 or 3 or 4 times stronger than a lot of these other variables, just depending on what it is. So while this is 0.703, product line is 0.195. So like the ability for product line to predict satisfaction is about as half as valuable to us or strong as, say, product quality, less than half even. Okay, so standardized coefficients are helpful because they tell us the magnitude of the influence, and they also tell us significance level. Now, so please understand the difference between the two. If I'm creating a model and I'm predicting satisfaction, then I use these unstandardized coefficients. If I'm testing the fit of the model and the value of these variables in explaining satisfaction, I use these standardized coefficients. The last part here that I'll mention is this partial correlation and what this is all about. So the partial correlation is the amount of variance explained by each individual variable. So you actually square these guys, the part portion, to get an understanding of how much value or how much variance is being explained in each one of these variables. So if we look at the part portion here, and if these numbers individually here were squared, then what you'd find is that some of these values are pretty small. So we mentioned X7, for instance, and we said that it didn't load particularly strongly. Now here, X7 has a fairly strong, it's significant, right? But when we come over here, the actual amount of information that's being provided by X7 is like saying 0.02 something something, percent of the variance. So it's pretty small. You could say the same thing. Look at this, 081 for order and billing. So what I'm saying here is I could probably take out X7 and X16, and we could probably, and it would probably be, we'd see a little bit of a drop in R squared, but probably not that much. And we would gain 2 degrees of freedom, and so we'd have a more parsimonious model. We'd have a better model, and we'd only have to give up a little bit of R squared is what my guess would be. And so we could actually try this. Analyze, and we'll regression, linear. All right, I took them out. X7, took that guy out, and then it was X16 was the other one. Took that guy out there. So so we actually have a 4 independent variable model here. I'm going to click OK. I'm going to run this. So now we have satisfaction, and then our 4. We have our correlations, 486, 603, 55. Those are good. We have this one inter-item correlation with the product line and complaint resolution. That's 561. That's a little high, but it is what it is. The 603 still, that's satisfaction. That's good. So not really a whole lot of that going on. Let's just drop down to the model. We have R and adjusted R square, so R is 877, adjusted R square is 759. So that's not any worse, or not much worse if it is at all, in terms of predictive ability. Yet we have, we took a third of the independent variables out. So that's good. That gives us degrees of freedom. That makes our measurements more efficient. F statistic is still strong. We have our new model here with all the variables are significant in predicting. The beta, the magnitude of the beta coefficient are significant, and everything's good. Yeah, so this is actually a better model. We created a better model by dropping those variables out. Okay, so this is multiple regression. So have any questions, please contact me. This will be a part of the job of your homework assignment, so make sure that you just walk through this, practice, get lots of data sets. We have lots of data sets available, so have fun testing and trying and doing whatever you can to kind of work on this. Okay? Thank you.